All right. Hi, everyone. Thank you for coming out on this Sunday morning. And as the title said, How I Learned to Stop Worrying and Love Deep Learning, a Radiologist's Perspective. So first, let's pause for an introduction. My name is Jaron. I like Python. I also like coffee, but mostly Python. I think I have to say that at the conference. I'm a radiologist here in Montreal, so at the McGill University Health Center. I'm an assistant professor of radiology. At the same time, I'm also doing a master's in health informatics at U of T. My clinical work is mostly concerning abdominal imaging, so interpreting CTs, ultrasounds, MRI examinations, a few procedures. My research interests include appropriate utilization of medical imaging, NLP, machine learning applications in radiology. More recently, I've been able to join the Canadian Association of Radiologists, AI working group, led by Ann Tang, actually one of the radiologists from UDM here in Montreal. So that's the CV. That's the official stuff. And then there's the other stuff that I do. So I organize a lot of the informatics and the research platforms within our department as well too. So that means engaging with, like local companies in Montreal and other organizations as well. But with Python, I got started in 2011. So I'm sure that everyone that's ever worked with Python, they've had their own import gravity moment. And for me, that would have been in 2011 when I was working on a radiation dose audit for my department. So I'm a big fan of the PyDICOM library. I was able to analyze a few thousand CT exams. Easy install was great. I was not using pip at that time. Everything's so simple, it just works. And since that time, I've built many things, but I promised in the abstract to talk about deep learning in radiology and cover these 5 topics. So part 1, the promise versus reality, healthcare, medical imaging, and AI. If you go on YouTube, there's a guy you may have heard of, Jeff Hinton. And there's a quotation that he's fond of saying, which goes as follows. I think that if you work as a radiologist, you're like Wile E. Coyote. I didn't know there was an E there. It was cool. In the cartoon. You're already over the edge of the cliff, but you haven't looked down. There's no ground underneath. It's just completely obvious that in 5 years, deep learning is going to do better than radiologists. It might be 10 years. Now, for the audience, this is about the point where you're allowed to go, ooh, or something along those lines, right? First off, as our neighbors to the south might put it, them's is fighting words. But when one of the pioneers of deep learning makes a quote like that, and you happen to be a radiologist, you should probably pay attention. Now, on the record, I don't feel like Wile E. Coyote. The image on the left is actually where the title, the Dr. Strangelove parody, comes from. But none of this stops that quote from being repeated or retweeted again and again. But I'll tell you something that not everybody does. Not everybody goes back to read the article, right? Because this quote comes from a New Yorker article that came out in April of this year. It's titled AI versus MD. If you haven't read it, definitely check it out. And there is a different quote, a less tweetable quote further down in the article. That's this. Early and accurate diagnosis is not a trivial problem. We can do better. Why not let machines help us? Because behind every quote, every network, every algorithm, there are real people with real illness, anxiety, suffering. And so whether you're a seamstress or a loom, whether you're DeepMind or you're a radiologist, the scale, the depth, the difficulty of radiology, healthcare, and medicine, it's endless. For every problem that we solve, 2 problems pop up in its place. And so why am I here? I'm here because you're all here. You folks are the builders, the people that will make the things that don't yet exist. And as much or as likely as little as I think from what I can do on my own, I've come to understand that maybe my role is not to build, but to get others to build with the radiology community, with the medical community. So that's what this talk is about. This talk is the half of me that serves, telling the half of me that builds, what should we do and how should we do it. Now, there's an assumption I'm making actually that you even know what a radiologist is. So if you Google that, you get this, a person who uses X-rays or other high energy radiation, especially a doctor specializing in radiology. So that's somewhat recursive of a definition. Now, if the phrase high energy radiation doesn't make you want to become a radiologist, I really don't know what else to say to you. But you'll notice one thing, right? Like the word really starts to take off after the turn of the 20th century in 1900, because that's around the time when X-rays were invented by Wilhelm Röntgen. Okay, so I think with a tremendous beard like that, we would gladly welcome Röntgen into the Python Unix sysop community, but different time. That hand with the wedding ring is his wife. That's the first X-ray published, taken on December 22nd, 1895. So if you jump to the 1950s, this is what radiology looks like. On the left there, we have some chest X-ray films. There's a nurse beside the radiologist helping to put up the films in the light box. And on the right, we have skull x-rays, something we don't even do anymore. And if you fast forward to 2017, this is more likely what the average radiology department of radiologists will look like. So it's dark. That's a long-running joke in medicine. We like dark rooms. Instead of films, we have LCD monitors. Instead of a nurse, we have a voice recognition microphone. But the task is pretty much the same, right? Because we're trying to take an image like this on the left and turn it into a report on the right like that. So there are standard headings like findings, which list all the observations you're making, conclusion of what you think the diagnosis is, recommendations, what you think should be done next. Now, for those who can read the fine print, that's actually an X-ray report of a dog, not a human, but the human reports look about the same. So you can't put up, privacy information. So the biggest reason why there is so much attention of artificial intelligence to radiology is probably because there's one word, DICOM, Digital Imaging and Communication in Medicine. So it's a standard released in 1985. That's like, for those keeping track, 15 years before Python 2, 5 years before Python 1, so it's very old. And it's important because it means that every digital medical imaging from 1985 to present is stored in one format. So to put it another way, DICOM is the JPEG of radiology. That sentence almost makes sense, except JPEG came out in 92. So really, JPEG is the DICOM of cat photos or whatever people do with JPEGs. DICOM is very, very old, which means I can very safely say, this is my quote, radiology is by far the most digital specialty in medicine. Super obvious, not very controversial. But that's the reason why everything that's happening with the resurgence of neural networks, deep learning, convolutional recurrent neural networks, ImageNet, AlexNet, GoogleNet, capsule networks, mobile app hot dog classifiers, all of this, even this, is relevant because radiology workflow is born digital, right? So you have a chest x-ray, a CT of a brain, ultrasound of a fetus, MRI of a liver, 3D CT angiogram of a heart. All these things are digital, which means that everything that's been learned, the miracle of ImageNet in 2012 and everything else, you can bring it upon the vast digital archives of radiology. It's my favorite William Gibson quote, "The future is already here, it's just not very evenly distributed." And medicine is pretty much the hallmark poster child of uneven distribution of technology. If you don't believe me, 4 words, we still use pagers. So it's 2017, people are live streaming over LTE with augmented reality, and there are infrared time-of-flight lasers unlocking phones with your face, and we still use pagers. So the logic goes, if you have enough data, you have enough layers, you have a DGX1 in your office, you have 1 or 2 grad students, 5 or 10 years, problem solved. Of course, a few of us don't think it's that simple, right? Some of us think that, all of us are betting actually on augmented radiology, so a future where, a combination of human and AI interpretation will happen concurrently. There's a quote, "The foreseeable future is not going to be human versus machine, but human plus machine, or human without a machine. And the human plus a machine is going to win." So that comes from Keith Dreyer, who is a radiologist, director of the Center of Clinical Data Science at Massachusetts General Hospital at Harvard. And so while our best minds are sorting this out, I'm worried about something else. I'm worried about the trough and whether we can even bring to fruition 10% of what is actually being promised. So that brings me to what is actually happening right now with deep learning in radiology. I'm going to review 3 clinical papers. These are excellent examples of where I think the whole field is going. And this is by no means exhaustive. This is 3 papers, right? There's many more in arXiv. There's many more that are being put out on Mackay, closer to the computer science field. But I think if we go through them, we'll begin to see some fixed and recurrent patterns, right? So our first paper concerns renal stones, which for those of you who aren't familiar with, these are calcifications your kidneys can produce. If one of these stones should obstruct your kidney, it's incredibly painful. We were actually taught that between child labor and stones, people would actually choose the child labor. That's just one factoid. Ordinarily, renal stones are diagnosed with a CT scan, which generates an image that you see there on the right-hand side with a little arrow conveniently pointing out the stone. You don't get that when you actually do the real work. This study was able to take 289 studies, 161 negative, 128 positive, and they kind of broke it down into 3 stages, right? They segmented the anatomy, where's the kidney, where's the bladder, where's the tube. They detected the stone, and they actually went one step above that. They actually figured out what the stone was made of, the chemical composition of it as well too. And you kind of notice there, the accuracy is between 82 to 97%, depends on the size. The smaller it is, the harder it is to find. These are not super impressive numbers, right? But it's actually pretty impressive that the machine had figured it out all on its own. The second paper comes from Thomas Jefferson University. This is actually regarding detection of tuberculosis. So they were actually able to fine-tune AlexNet and GoogleNet to get an AUC of 0.98 on a limited case series of a few hundred of cases. So the highlighting that you see there actually is where the bright red and the bright blue, that's where the network suspects that there is possibly TB. So that's fairly interesting. The thing that's cool about this paper is that there is this idea of an AI screening pattern, right? Because TB prevalent regions that may not have access to a human radiologist may benefit from an initial automated diagnostic screening, and then more equivocal or more borderline cases can be sent for an expert to reevaluate or to verify. So I think this pattern we're going to see a lot more of in the future. And the last article there is something called ChexNet, C-H-E-X-N-E-T. This actually came out 2 days ago on Archive, okay? So you might recognize one of the names at the end there, Andrew Ng, also of pioneering deep learning fame. I would be remiss to mention this article without mentioning the data set that actually makes it possible, right? Because the data set actually comes from the NIH by a researcher named Ronald Summers, who actually managed to release over 100,000 chest x-ray images, anonymized of course, of almost 30,000 unique patients with 14 categories and labels that are on there. And this is actually download. If you just research or just Google some of these terms, you can actually download this yourself off of Dropbox. And this is like one of the largest sets that's been released publicly. So what Ng and the rest of the collaborators were able to do is that using ChexNet, they made a test. They trained on the remainder of the set, right? And they used a concordance between multiple human reviewers to see where they agreed on the labels, and then that's how they made their ground truth. And the performance that they put out actually says that they have a model that is either at or exceeds kind of human performance. So the 3 humans, you can see the red X is there. The green one is the average of the humans, and that's the receiver operative curve, which is almost like at the line or a tiny bit of left towards the top left corner. So that's getting to be very interesting. And when you look at the sub-results of the 14 labels, some of this actually has some face validity to it. So the easier things at the bottom, like a hernia, which is this where a portion of your intestines and your stomach actually kind of push up into the chest, right? That's a very easy thing to find, 0.93. An infiltration, which is where you have, it's a little bit cloudy on one side or another, a little bit harder to define, right? 0.72. So some of the rankings internally seem to actually make a lot of sense as well. Now, there's been some critiques of the paper, and one of the things that's very important to mention is that it's possible for 2 diseases to have an identical appearance. So I can give you an image like this, and depending upon whether you were coughing, you had a fever, or whether, let's say, you were in a bicycle accident, you got hit in the chest as well, the actual diagnosis may vary. And that's something that's a little bit more difficult to appreciate from a non-medical perspective, right? But still very, very interesting work. Now, you'll notice all of these concern image interpretation. So there are other things that happen around the process as well, too. So there are events that have to occur before the exam, after the examination. And the thing that I find kind of interesting is that there are a lot of other practical problems that actually need AI, need solutions, right? So if I ask you questions like, what if a system could predict whether a patient was likely to not show up to an exam? Right? If we could predict that, wouldn't that be useful? What if we had an algorithm that you enter in the symptoms and you actually can tell an ER doctor the right test, or maybe not to order an examination, could actually save the healthcare system some money. Or let's say you could predict the probability that an exam would be positive or negative before you even performed it, so you could actually order rank them, schedule the high and the ones where you're more likely to find something earlier on, and the ones that are less likely to yield an answer further back. So there's all these other things that don't even touch image interpretation, and there's a lot of other possibilities that can be performed as well too. And the thing is that these other ideas could actually be easier, more doable. They could actually incur substantially less commercial liability as well, because they're more operational as opposed to regarding the actual image interpretation. So I did promise the BuzzFeed component, like the top 5 things you must know before designing a system. And when you see a lot of talks like this, usually they talk about FDA device approval, medical legal issues, so those are very important. But the things I'm going to bring up are a little bit more fundamental. So number 1, healthcare is not a game. So when I say that, I don't mean that it's serious business, it's life and death. I actually mean the machine learning definition of a game. So there's a great article from KD Nuggets, it's a data science website, that makes a point about the importance of data sets versus algorithms. The key point it's trying to make is that actually sometimes the distance in time between the major breakthrough and the data set is 6 times shorter than between the breakthrough and the underlying algorithm. So for example, convolutional neural networks, in some form they've existed since 1989, but the major leap forward was the creation of ImageNet, the labels, in 2010. Of course, that's an oversimplification because a lot happened between 89 and 2010, but it's an interesting point because you could ask, what is it that we could be doing with the algorithms that we already have, but we can't because we don't have the right data set, the right labels? That's a pretty huge and crazy idea because it means that if only we had the labels, we could make some very, very cool stuff. But there's a counter problem. There's a term, a wicked problem. Okay, so this term wicked problems, it's coined by two researchers, Rittel and Weber in '73. They were actually talking about management and social policy here. When they say wicked, they don't mean evil. They mean resistant to resolution. Almost like that consultancy project with a bad client that never seems to end. It keeps on having feature creep. So kind of like that. That's a wicked problem. I'm sure some of you have experienced that. And there's a list of criteria of when you know you have a wicked problem. And I've highlighted some of them in the list. And a lot of this reminds me of things in healthcare. So when we make a diagnosis, oftentimes we don't know whether we were right or wrong immediately. We lack an immediate solution. So you can't treat patients by trial and error. Sometimes you only have one shot. Are you going to take that appendix out or you're not? You have to decide right now. Every person is unique. Every disease sometimes is unique. There's sometimes multiple explanations. You don't know which one is the most important. I highlighted number 10. Planners have no right to be wrong because they're responsible for outcomes that result from their actions. We call that malpractice insurance. You can do everything right, something bad could still happen, and you're still responsible. That's the definition of the practice of medicine. So healthcare has a lot of elements of being a wicked problem. You know, in a chess game, you know who wins or loses, and you can simulate a Go match 1 billion times and reinforce your learning. But medicine doesn't always have an answer key. Sometimes it does, sometimes it doesn't. And if you don't have an answer key, or even worse, if you have the wrong answer key, backprop isn't going to work. The standard techniques aren't going to work. So we need more labeled data sets. We need more of them. We need them to be open, standardized. We need better tools that actually work with the existing clinical workflow so we can extract all of the labels out from the work that we're already doing. We need advanced unsupervised machine learning methods. We also have to be very clear about the scope of problems. Certain things are more approachable, certain things aren't. And it's hard to make large blanket statements. Number 2, the biggest feature is speed. Okay. So you see a lot of articles about changing healthcare, and changing healthcare is very, very hard. That healthcare practitioners are very resistant to change. My favorite image regarding change in technology is from this one here. Is like from 2005 versus 2013. The people in Rome waiting for a new pope. Okay, I think there's one razor in the bottom right corner there, right? And obviously it's very different in 2013. So obviously you didn't have to incent these people to bring out their phones. Here's a chart from the U.S. Center for Disease Control and Prevention. This is a CDC chart. Anybody know what this shows? Or close? Well, syphilis. This is the U.S. rate of syphilis from 1941 to 1999. So you could ask, what happens in around 1946? Well, that's when we figured out how to mass produce penicillin, like a lot of it. And you could be asking, so what does syphilis have to do with deep learning? Don't answer that question. Medicine isn't resistant to change, okay? So far from it, right? When something works and it works well, medicine changes very, very fast, actually in 5 years, okay? But you just have to make sure that what you're proposing really, really works. So we talk about accuracy, sensitivity, specificity, but there's one feature we don't spend as much time on, which is speed. So those of you that are in the UI, UX business, you kind of know this, right? Speed matters. And the same rules that govern user satisfaction of your website, they apply from a medical perspective as well. So a single individual can have per CT or MRI almost 400 images per exam. At McGill, actually, some of our protocols go up to almost 2,000 images for one study. That's out of like 50 patients per day. So you only have about 2 or 6 seconds per image. And so I can tell you that if your AI solution results in spending 2 or 3 times as much time, you will encounter resistance to change. So we need offline pre-processing. We need active learning systems that will, have an automated mistake, correct itself once, and not happen again. We need error prevention so that we can, sustain quality despite the high volumes, and also triage systems to choose, which one of the 50 is going to be the most important to report right now. Number 3, privacy is king. So it's all very obvious. Health privacy, very, very important, especially when you're dealing with the scale of the data that we're working with. And we need standardized policies and tools that help with anonymization. This is actually very, very tough for us right now, okay? We need to utilize almost like privacy preserving methods so that if we want to train and utilize AWS or the cloud, we can do that. Currently, right now, we can't. It's actually quite difficult. So we need to figure out labeling at scale. So for ImageNet, One of the major breakthroughs there is that they use Mechanical Turk to help with the labeling. We don't have the same option with that, and so we need more creative workarounds in order to fix that problem. And we need to ensure anonymization at an image level. So sometimes you can strip out all of the headers, all of the tags, but there's still someone's name directly in the image. That's very, very hard to control for us. And the last, so number 4, plumbing before rockets. So this is the Civilization 5 tech tree. We have nuclear fusion on the right and the very popular animal husbandry on the left, okay? In order for things to progress, you always build atop previous innovations, right? So with radiology, there's obviously a lot of technology, but not all of it is the right technology. So a lot of the ideas in infrastructure are as old as the CRT monitors in that flowchart would suggest. So at McGill, we have, our archive is about 650 terabytes, right? But try to export tens of thousands of them in a research project, and you might be waiting for a while in order to get that information. So we have volume, but we don't necessarily have velocity. And it's a common issue across many hospitals, many sites. And it's quite difficult to get those large data sets for your project. So we need infrastructure that builds on top and complements existing infrastructure, and actually tools to help sub-select the cohort so you don't have to export as much. The last point, very, very clinical. An area under a curve and clinical usefulness aren't necessarily the same thing. So you could have an algorithm that is, by computer science standards, state of the art, but practically it may not affect how care is being delivered. So an example is, let's say you have an algorithm that can predict what kind of tumor that is. Well, the practical ramification is that the oncologists, so the cancer doctors, they're still gonna want a biopsy of that to be able to do the testing, to be able to confirm diagnosis. So like 95%, 97%, it's not gonna be good enough. And so the impact of that algorithm may not be as great as everyone's going to predict that it is. But here's the thing, this is the good news. If you change your question, so let's say you're trying to predict, for example, same situation, but you don't want to predict the overall prognosis and life expectancy of a person, then suddenly actually that enters into the decision making, right? You can decide whether it's worth it to undergo the surgery, undergo the chemo as well too. So there's a lot of domain knowledge that's plugged in there that if you just change one variable, the algorithm is the same, but in one situation it's useful and in another situation it may not be. So that's a very subtle point, but I think it's also pretty important to mention as well too. So datasets and Python resources for medical imaging, the usual suspects, right? So all the usual libraries, I'm sure everyone's very, very well aware of it. The thing that is a little bit more specific to this talk is the datasets and the labels. Those are a little bit harder to obtain. So I have some links up here. I've kind of pointed to the original CHESS dataset as well too. There's a group, Radiology Data Quest, that blog has some interesting articles if you're just getting started with image processing. And there's the NIH link at the back. My intention is actually a lot of this stuff with the talk, the links and the references, I'm going to try to post up, so ratnet.org. I'm hoping that we can actually start, collecting the public data sets and start, accessing them so that we can actually start sharing it more easily. Because right now it's quite difficult. You have to jump from place to place to place. It's very hard to find the right data. And so I'm working on that, but hopefully we can move that forward. So I'm going to return back to those two quotes. It's not obvious to me that we're going to be done in 5 or 10 or 50 years, right? But it is obvious to me that we need to get moving, okay? It's obvious to me that this is not a job for one person or one lab or one company. It's going to take a lot of people. It's going to take all of us. And I aim to convince you of anything. It's that, it's that we do these things not because they're difficult, not because they're easy, but because they're difficult. The work is hard. But this work really, because of the application, it's worth it, right? And you really, really have to be a part of this. Those machines are not going to code themselves. Thank you very much, guys.
Thank you, Jaron, for the great talk. We have a few minutes for questions. Are there any questions for Jaron today?
Yeah, sure.
I used to do medical imaging research, and I got out of it because I realized the bottleneck is actually not deep learning. The bottleneck is politics.
Okay.
And getting to the data. And what can you do to make the government realize how important it is to make this data available? I would really love to see something like donate your data to science, where you go
Right,
your
right.
open note card, check off, I want all my medical imaging data to go to research to be anonymized.
Okay, that's a really cool question, because I've actually had discussions with the department and with the Research Institute at MEHC and so forth regarding that. It's a complex issue because you can look at it from two ways, right? You can look at it from the public and the research perspective, but most importantly, you also have to look at it from the individual patient rights perspective as well, right? we have so many newspaper examples of privacy breaches, of data breaches, and so forth that are unintended, right? But also quite dangerous as well too. And when you make a mistake regarding that kind of governance and that policy, right? You only get to make that mistake once. You only get to be on the Gazette once, and then after that, you can't really go back on there again as well too. So the models that we're working on right now, if it's internal within a hospital, it falls under a standard IRB or an REB, so we can do larger exports because it's internally hosted. The big problem that we're having with AI and deep learning is that the engineering expertise in order to run these projects, they don't exist necessarily within the medical field, or even if you extend out to the computer science field as well too, it's harder to get collaborators. People are very busy with their own projects as well. The model that I think is the most promising, it actually borrows it from pathology, which is a biobank model, which is that when patients come in and are registered under a specific, let's say a tumor bank, a certain kind of a disease as well too, they're able to actually give their authorization on the opt-in system, right? That has a full consent for using it for these reasons. And so we're actually in talks with pathology to try to take their processes and try to mirror it as well. So instead of a tissue bank, you actually have an image bank. The disadvantage with that is that there's a lot of retrospective information that we're not really taking advantage of. And so that's a little bit tougher. And really across both US and Canada, the policies aren't very, very clear, but it's something that the Canadian Association of Radiologists, CAR, we're trying to work on to figure out what is the right thing to be able to do. But I think the safest way so far that we've seen is a biobank method where people opt in and it's a fixed registry. Yep.
Next question.
Yeah. So speaking of the biobank method, how do you avoid a Henrietta Lacks type situation where you have all these sort of ethical considerations that might not be considered yet? Obviously, the IRB process can look retrospectively at the bad things that researchers have done in the past and say, don't do those things. Yep. But what sort of things can we expect in the future as we move more to a data-driven diagnostic model?
Right. So the example of HeLa is pretty interesting regarding that. The issue is always kind of come down to so the section that we gave in the top 5 regarding privacy and anonymization, right? So that needs to be handled very, very carefully and very, very properly as well too. So even second order meta information like timestamps, sequences of events, or you can actually reverse engineer from those as well. So there are ways. I think from a technical perspective, it's possible as well too. From a more I guess a very practical perspective as well too. Where the model that we're using to engage with other collaborators, right, is that we're actually looking for not cloud, obviously, for ways to bring in and support within the research institute, within the lab, the hardware being brought into hospital as well too. So so for companies that want to try out something as well too, we can do it in an internal or a safe controlled environment where we know it's behind firewall, it's behind network as well too. There's also kind of almost like a staged degree of kind of engagement and trust where the initial data set is much smaller, you scale it up as it gets larger and larger and larger. But there are boundaries to those issues that aren't very clearly specified now regarding that kind of an engagement. The model works better when it's between an academic and an academic institute, so there's lots of really great precedent for that. But regarding private organizations, it's actually not that clear.
We have time for one more question.
Yeah, last month I wanted to volunteer for PyCon, so I met the president, Francis, and at that day I got huge pain in my bowel. I ended up in the emergency the day after, okay. And I got a scanner on Friday, my bowel. So I think my bowel is in your archive somewhere at McGill. And well, I got to see 2 doctors. This was a public holiday, so it was Saturday, Friday, and then Monday. But nothing except pain for 2.5 days. And then I got a second scanner on Sunday, so 2 days later. And then the surgeon said, okay, you're gonna go to surgery in 2 hours. And I wonder, so you have McGill has this kind of data set today in the archive. I wonder if the AI would have detected the problem in the first scanner.
Right.
And my second question is, when does AI goes to McGill, CUSM, and Montreal Hospital?
Mm-hmm. Okay. Okay, so we'll address those 2 questions in sequence. So the first question, actually, it's kind of interesting, right? Which is, can assisted analysis find something earlier then? So I'm not sure for the specifics of your situation as well too. There are some research papers that do show that sometimes an earlier change can be more sensitive when it's with assistance as well. There are practical concerns because a lot of times it takes a lot of more analysis, more segmentation, right, in order to become, so you get more sensitivity, but you have to almost invest a lot more time into the analysis. So there are some solutions that are on the edge. I think that overall, it's kind of like that Keith Dreyer quote as well too. If you have assistance, I mean, if it's bad assistance, you can always choose to ignore it, right? But in conjunction, if it could warn you of something earlier, right, there is some evidence that shows that that is possible, right, and would definitely be useful. One of the applications that I'm actually really interested in actually is regarding error prevention, right? Because if you have an assistance with you as well too, maybe something that you wouldn't be, able to notice within your 2 to 6 seconds, you can actually pick up, and that would actually create an overall a higher quality interpretation. Now, regarding your second question, which is when is it coming? Okay, the thing that this is more for the medical audience as opposed to the computer science audience as well too. When we do voice rec, right? Technically, that's sort of AI derived, right? Like there is AI in different places at different levels, right? So the world is heterogeneous, right? There are technologies that are in different places. So Massachusetts General, they have more AI, they have less AI. So and the thing is that it's not going to be this big bang thing where like it suddenly gets turned on, right? It's going to come on in different speeds in different places as well too. So there, in my opinion, actually, there already is AI within radiology. There probably is at UDM, at SHIM, and so forth, right? But it's just in different applications. And so one of the terms that you see oftentimes used is this concept of narrow versus general AI as well. And you're going to see more and more narrow applications come in bit by bit. A lot of how that will happen, how fast that will happen, and where it will happen, it depends on the community efforts, right? Because I can see it going down in one way where you have like if it's highly privatized and if it's only a few entities have it, then the access is going to be poor. I can see another version where if there are lots of little open source modules as well too, then you can kind of mix and match, and then distribution could be very good. So there are a lot of possible futures that could happen, and none of that is set in stone yet. That's one of the reasons why you want to engage with the community and get people to help you out.
Thank you again, Jaron, for the great talk.
Yeah, thank you.